All right, hey guys, this is going to be a start of a series of videos just to help with Physics 114. Or for those of you not in 114, just E&M, electricity and magnetism. So I'll just be going over each of the workshops, just the topics and basic formulas that we covered in each of the workshops. And then each video will be about 10-20 minutes long. And I'll just be going over everything we did in the workshop. So this week, or today actually, I'll be starting with theory of relativity. All right, so one of the most basic things that we'll start off with in any physics, not just physics, E&M, is the idea of a frame of reference. And what a frame of reference is basically, you can think about it as a set or a setting in which all the basic laws of physics apply. So, for example, right, if we have a car moving, and I'm going to represent a car moving as a box, and the car is moving at 30 miles an hour. And then we have another car moving behind it at 20 miles an hour. And we have a person standing right here, right? So each of these individuals or objects can be thought of as a frame of reference, right? So if we have the person standing here, right, we look at the frame of reference, at this person's frame of reference, this car, car one, let's call it, is moving at 20 miles an hour, and this car two, is moving at 30 miles an hour, right? But if we're in the frame of reference of car one, car two looks like it's moving at 10 miles an hour, right? Where if this car is moving at 20 miles an hour, right, this car is moving 10 miles an hour faster, right? And if this car doesn't know it's moving, which it won't, you won't be able to tell if you're in car one, you would think that this car is moving at 10 miles an hour, right? So it is all relative. So for example, car two would think that car one is moving 10 miles an hour in the opposite direction because it's getting further apart from car one, right? So it's all about the frame of reference. And the important thing to understand about frames of reference is when we have a frame of reference that's moving like we did in the car example, that's moving at a constant velocity. So frame of reference at a constant velocity, we refer to that as an inertial frame of reference. So what's so special about an inertial frame of reference? In all inertial frames of reference, the laws of physics are all the same. I'll explain what that means in a second. And the speed of light is the same. Or is constant. Right. And so we can call this statement one, statement two. What I mean by the laws of physics are all the same is basically everything you learn in physics up to this point, everything you learn of the Newtonian physics where F equals ma, or A equals 1/2 VT squared plus V initial T plus X initial. All those formulas you've used so far stay true in any inertial frame of reference. And number two, which is the weird one, is that the speed of light is constant. So we know, right, the speed of light c, or we call it variable c, to denote the speed of light, is 3 times 10 to the 8th meters per second, approximately. right? And this stays constant in every frame of reference. And that may seem a little bit weird, right? So when we talked about the example before with the cars moving, we had car 1 moving at, I think it was 20 miles an hour, and car 2 moving at 30 miles an hour, right? Car 2 appeared to car 1 and moving at 10 miles an hour, right? So if we want to phrase this another way, or redraw this, if car 1 was stationary, car 2, or if we want to represent car 1 as stationary, car 2 would moving at 10 miles per hour, right? But this isn't the case with the speed of light. So we have, say we have an object moving at the speed of light, or we have a particle light moving at the speed of light, right? A photon moving at c. No matter how fast car 1 is moving, right, this object is going to be appearing to move at c. So if this is moving at even like 2 times 10 to the 8th meters per second, this is still going to be moving. This is still going to appear to be moving at 3 times 10 to the 8th meters per second relative to this, right? So no matter how fast this is going, this is not going to look like it's decreasing in speed at all. The speed of light is constant in any inertial frame of reference. So that causes some weird things. What we call, or two things called time dilation. One, the time dilation, which is the idea time moves slower in a moving reference frame. And the other thing that happens is what we call length contraction. Which is that length shortens in a moving reference frame. And I'm just going to reference reference frame as RF. Right, so what exactly do these things mean? And how do we equate these things? How do we look at this mathematically? So one thing you have to understand is gamma factor, right? And gamma, represented by this symbol here, is equal to 1 over the square root of 1 minus v squared over c squared. Right, so the first one I talked about, we talked about time dilation, right? Where delta t, or your change in time, is going to be equal to delta t naught, delta t naught times gamma, right? And if I just substitute gamma in there, delta t naught over the square root of 1 minus v squared over c squared. So how do I apply this to formulas? So basically this delta t naught is what we call proper time. And proper time is the shortest time between any events that any observer can measure. How another way it's described is the time, or it's called proper time because it is the time measured if an object is in a non-moving reference frame. So for example, to explain that, okay, so one way we can explain proper time is we had an observer on Earth, right? I'm represented that by a square, and then a spaceship that took off. And this was an actual experiment done. And they had 2 synchronized atomic clocks, right? And the clock on the spaceship obviously was moving at a very high speed, very high velocity, right? And the clock on Earth was at rest, it was not moving. So when they came back, right, and they checked the clock on the spaceship, the atomic clock, which measured time very precisely, showed to be slower than the clock on Earth, by exactly the amount of time that was predicted by these equations, right? And so the proper time in this case is the time on Earth, because this was not in a moving reference frame. Or in other words, your delta T naught will always be smaller than your delta T. Delta T will always be larger than delta T naught. And the way we can see this is that, as you see here on Earth, we don't have much things that can move close to the speed of light, right? V generally is going to be very, very, very much smaller than the speed of light, right? So when we have delta T, this gamma factor, right, 1 over the square root of 1 minus V squared over C squared, this part of the denominator will essentially be 0. So you'll have 1 over the square root of 1, you'll have 1, right? So on Earth, most things are equivalent. Delta T naught and delta T are equivalent, right? As we get closer to the speed of light, right, that's when things start to get a little messed up, right? So as we get closer to this approaching 1, the denominator will reach 0, right? And then anything divided by 0, or anything divided by a really small number is really large. So delta T will become really large. So delta T naught will be a small number, and delta T will be a larger number. So keep that in mind whenever you're doing problems, to make sure that when you're plugging the appropriate numbers into delta T and delta T naught, that you get a larger number for delta T always than delta T naught. So now if we look at the other phenomenon we talked about, which is length contraction, we have, in this case, D is equal to D D naught divided by gamma, where D is distance or length. And what this means is the length, as we talked about, the length of an object in a moving reference frame is presented to be shorter than when it is at rest, right? So when you have something moving at a very, very high speed, close to the speed of light, your D will get longer. All right. Just like our T naught, right, was proper time, our D naught or L naught is proper length. Right. So where D naught or L naught will be the shortest distance between between events, or shortest distance between any 2 points that an observer can measure. Okay, so the next thing I'm going to cover is what is called Galilean transformation equations. So I'm going to draw 2 reference frames, right? We'll call first reference frame if x and y. We'll call this S, right? And then we have a second reference frame that's moving at a velocity v, and we'll call that, so it starts at the position that the resting frame is, right, and it's moving. So think of a car starting at a certain point with an observer, and then the car starts taking off, right? We call that S prime, right? So we have S and S prime, so this will be Y prime, X prime. So if we have this moving reference frame, right, and this, let's say this moving reference frame is moving at a velocity v, the distance between these two will be vt, right, because distance equals velocity times time. Now let's say I have a point P here, right, in the moving reference frame. So think about somebody in this car. This person is now x prime away from the start of this axis, right? And this total distance here is x, right? If we're looking from this reference frame, right? So if we start looking at the variables, we have x equals x prime plus vt, right? And since we're going to be looking at this reference frame, we'll call this vt prime. And not a big difference because t is equivalent to t prime, right? Because we're just measuring time at the start of when the car starts moving. So our t and t prime are equivalent. And now we have no difference in the y and z directions, right? So y is equal to y prime, our z is equal to z prime, and our t, like I said before, is equal to t prime. Right? So not too difficult. So this is just, these are equations you would just use if you have a moving reference frame, right? And you want to relate the moving reference frame back to the non-moving reference frame. Okay, so now let's a little further. Let's say P starts moving, right? And we'll say P moves in a direction, in the x direction at a speed of u prime x. In the x direction, u prime y in the y direction, and u prime z in the z direction. And I'm saying that it's moving in the u prime x, u prime y, u prime z in reference to the moving reference frame, right? So I'm saying P is moving at this velocity in reference to the moving reference frame. So let's say, pretend it's a bus that's moving. My point P is now moving or walking up to the front of the bus, right? At a speed of u prime x in the x direction, u prime y in the y direction, and u prime z in the z direction, right? And now we've said that y and y prime are equivalent and z prime are equivalent. So we know that u prime y will equal uy and u prime z will equal uz, right? So the only thing that's different is the u prime x, right? So how fast is this moving in terms of ux, or how do we relate this to ux, right? It's pretty simple. All we say is in terms of the standard reference frame that's not moving, u prime x plus v, however fast this bus is moving or however fast this reference frame is moving, is equal to ux, right? So basically all this equation is saying, right, is if a person is standing here, how fast do they see a person on the bus moving if the bus wasn't there, right? If the bus was like invisible or transparent or something like that, how fast is this person? Let me draw this a little more clearly. You have a person standing here and a bus moving at speed v, the person moving at speed u prime of x in reference to the bus. How fast does this person see? This person sees him moving however fast he's moving plus the speed of the bus. Right, so pretty simple. Now things get a little weird, like as we said before, when people, now no person is going to move at the speed of light, but for example, if some of the numbers in this equation start approaching the speed of light, or v approaches the speed of light, right, the numbers get a little weird. And I'll show you the equations for those. It's not really important the derivation, just more important how you derive the formulas. If you want to relate, so if we have a standard moving reference frame, and someone's moving close to the speed of light, we say that he's moving x times is equal to gamma times x prime plus v t prime, right? So however fast the moving reference frame is moving, plus, so this is, remember, this equation is almost the same as the one before, so you just multiply a gamma factor, right? And if he's not changing in the y direction or the z direction, these stay constant, right? And our time also, it's a little weird, where t equals gamma, sorry, t plus vx over c squared, right? So remember, x is always in reference to s, which is our non-moving reference frame. Anything with a prime, so x prime, y prime, z prime, we're talking about our moving reference frame, right? And then v is how fast s prime is moving. So how fast s prime is moving. So how fast is our moving reference frame moving? So one more equation we'll look over, right, is what is called Lorentz velocity transformation. And I'm just going to show you the formulas where u x is equal to u prime x plus v over 1 plus v u prime x over c squared. Our uy equal to u prime y times the square root of 1 v squared over c squared. 1 plus v u prime x over c squared. And our uz is equal to u prime z squared of 1 minus v squared c squared over 1 plus v u prime x over c squared. Right, so these will be used in equations where you have an object moving in both x, y, and z direction. So I'll give you an example of using this formula, right? So let's say we have a problem here where we have Earth, and leaving Earth, we have a rocket ship traveling at a speed of v equals 0.6 c, right? So 6/10 the speed of light. And at a certain point, rocket 1 releases another rocket called rocket 2, right? That's traveling at a speed of 0.6 c with respect to rocket 1. Right. So how do we use the formula, or the formulas that I just went over, to figure out what, the speed, I want to figure out what the speed of rocket 2 is with respect to Earth. Sorry. So what is the speed of rocket 2 with respect to Earth? Right, so let's try to figure out what our moving reference frame is, our standard reference frame is, what is moving, what's not moving, and then try to figure out from there. Right, so let me write down the equation. So u of x, right? So we'll assume this is all on a straight line, right? So we can just use x, and we'll say x is our x is the axis that's going on. So pretend that this is all in a straight line and x is the axis. So we say u of x equals u prime x plus v over 1 plus v u prime of x over c squared. Right? Remember, u of x is our non-moving reference frame. U prime of x is our moving reference frame. V is how fast moving reference frame is moving. Right? So we have the Earth, right? This is stationary, so we'll call this u of x, or in my drawing before, we said this was s, right? This is our moving reference frame, right? Because we have the velocity of this in the problem before, we had a point P moving with respect to the moving reference frame, right? This is our moving reference frame, s prime, right? Or u prime of x. So if we plug all this information into the problem, u of x, right, which is what? U of x is how fast our point P is moving with reference to the standard reference frame, right? U of x is equal to u prime of x. So how fast is, u prime of x is how fast our point P is moving with respect to the moving reference frame. So our 0.6c plus v, and what is v? How fast is our moving reference frame moving? Also 0.6c over 1 plus v. So what is v? V is how fast is our standard reference frame moving? 0.6 c. U prime of x is how fast our point P is moving with reference to our moving reference frame, so 0.6 c again, all over c squared. And if you solve that out, you get 0.88 c. Right, so notice how this is different because we have objects moving very, very fast, right, to what you would expect, right? So if I had, pretend instead of 0.6c, 0.6c, right? Let's say I had, think about a person, right? Remember our answer is 0.88c, meaning that rocket 2 is moving 0.88c to someone who is observing on Earth. So if someone on Earth is observing how fast rocket 2 is moving, they would record rocket's 2 speed to be 0.88c. Now notice how that's different from Galilean transformations, right? What we did, right? So if we have a person and we have a car moving, let's say 0.6 miles per hour, right? And then we had another car moving 0.6 miles per hour with reference to car 1. A person on Earth would simply say u of x is equal to u prime x plus v. And so how fast is this moving? 0.6. 0.6 coming from how fast is our object moving with reference to reference frame 1? 0.6 miles per hour. Plus how fast is our moving reference frame moving? Also 0.6 miles per hour. So equals 1.2 miles per hour. Right, so we just simply add them here, but we can't do that for here, right? So if I were to answer this question in terms of Galilean transformations, I would say rocket 2 is moving at 1.2 c, right? Which means it's moving faster than the speed of light, which we know is not possible. So remember, if things are moving close to the speed of light, we have to use Lorentz velocity transformations. The last thing I'm going to cover are just some basic formulas called Doppler shift. And Doppler shift is basically the change in frequency or wavelength of things moving towards each other. So if we have a source and observer moving towards each other, we have two formulas, right? And this doesn't necessarily mean that the source, and by source I mean whatever's emitting a light or sound, right? Anything like that, anything emitting a wavelength or a frequency, the source and observer both don't have to be moving, right? Either the observer can move to the source can be moving to the observer, or both are moving, right? We have our lambda equals lambda naught over C minus V over C plus V, right? And our frequency is equal to C over lambda equals F prime square root of C plus V or C minus V, right? So what do these things mean? So our lambda is our wavelength. A lambda naught would be what the wavelength would be if the source was not moving. Same thing with F naught, what the frequency would be if this frequency or the source is not moving. Our V are the velocities that the source and observers are moving towards each other, right? So if we have an object moving 8 miles an hour towards another object, right? Our V would be 8 miles an hour, right? But if this is also moving at 8 miles an hour, you can consider themselves moving towards each other at 16 miles an hour, right? Because this is essentially the same thing as saying one source is moving towards the other at 16 miles an hour. Right, so that's our V, and our C, of course, is speed of light. So 3 times 10 to the 8th meters per second, sorry. And if they're moving away from each other, we have pretty similar set of formulas. Lambda equals lambda naught, C plus V, C minus V, and F equals F naught over C minus V over C plus V. So that's all I had for this video. If you found this helpful, I will be uploading more videos about different topics throughout Physics 114, probably once every 1 to 2 days. So feel free to subscribe. And if you have any questions, put them in the comments and I'll try my best to respond to them as soon as possible. All right, thanks for watching, guys.